So yeah, the point is, there are many ways to sample one bit in like steps, and those are, I will mainly focus on this way, which is kind of a canonical way to sample a bit continuously. And by continuously, I mean that, the expected entropy gain that you have in every infinitesimal time change dt is also infinitesimal. So you kind of, you generate the bits continuously rather than, in discrete steps. Okay, so let's focus on this, and first let's try to prove that such a thing actually exists, such a martingale. So, what we want is the following thing. We have, so this is our time. It goes from 0 to 1, and this axis is like, the value of xt. This is t, and we want a process that is always either equal to plus t or minus t. So it always stays on one of these two lines. But since it's a martingale, it has to jump between the two. So, it's probably gonna look like this. It like jumps between them, and then maybe it stays on this one for a bit, and then, it jumps up here, and then it stays on this one for a bit, and then it jumps down, etc. So this is the graph of xt. And, in the end, it ends up at either like plus or minus. And, the reason it has to jump is once it got here, it is a martingale, right? So the probability to get to, plus and minus 1, given that you are like here at some value alpha, must be proportional to, the ratio between like these two intervals, right? I mean, it has to be that the expectation of x1 given xt is xt. So basically, whether I'm on this line and on this line, and if I know t, it uniquely defines, what the probabilities are to reach plus or minus 1 in the end. And it also uniquely defines uniquely determines, the probabilities to reach like plus or minus. So suppose here this is xs. So for any t bigger than s, this is some t bigger than s, the probability to be either here or here is uniquely determined by, what xs is, whether or not it's plus s or minus s. And in general, this process is also uniquely defined. And I guess one way to think about this process is you can take actually a Brownian motion. So this is the Brownian motion bt, and then you can define a continuous family of stopping times. Tau of t is just the minimal value of s such that b of s in absolute value is equal to t. So, for every t, I look at the first time that the Brownian motion reaches the value t, in absolute value. So I get some, sequence of stopping times. Maybe it's here, 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 and then these ones, and then I don't know, these ones or whatever, and then here. And then I can just define xt is the Brownian motion at tau of t. And this will give me a process that, satisfies these two properties. Or we can just actually define it directly by basically calculating what the probability is to jump between this line and this line at any given instant. So, like, suppose xt is equal to plus t for some t. Then now consider the distribution of xt plus dt conditioned on xt. So here I'm not going to be completely rigorous. And from now on, what I wanna, so dt is infinitesimal, and everything is kind of on a continuous time scale. But from now on, we'll do everything only semi-rigorously, and we'll just imagine, or not imagine, we'll just say, we'll fix a small number and say that dt is not infinitesimal, it's just 1 over a million. Okay, and we'll only evaluate our processes on, so we'll only consider the case where t is some multiple of dt. So t will always be, in z times dt. I think this is a really good way to kind of factor out all the extra technical work you have to do in order to make things, really work in continuous time. So we'll do all sorts of heuristic calculations, but everything is going to be correct in the limit. I just don't want to waste time going to the limit. So, okay. So this was kind of in parentheses, and now consider the distribution of x at time t plus dt given xt. So, x t plus dt is going to be equal to either plus t plus dt, and this is going to happen with probability some p that we'll calculate soon, or minus t plus dt, and this is going to happen with probability 1 minus p. And now let's try to understand what the value of p should be. Okay, so we know that xt has to be a martingale, meaning that the expectation of xt plus dt is equal to conditioned on xt, has to be equal to xt, which we assumed is equal to, actually, maybe let's even do it in general. So this is to be equal to xt, which is either plus or minus t, right? And on the other hand, this is equal to, p times t plus dt plus 1 minus p times minus t plus dt. Okay, let's actually assume this is equal to plus t, as we wrote above.
In the second case, should it be minus t minus dt? Because the negative of
minus t, sorry, the minuses. Sorry. Sure. And now, let's just solve these equations. And if we solve these equations, we get basically that p is equal to actually, maybe, sorry, let me flip the roles, because let me call this 1 minus p and this p, because I want p to be the probability to actually make a jump. Sorry, I just flipped the roles of these two. So, this event is it just means that, xt jumps, the process xt jumps between time t and time t plus dt, right? And like this event corresponds to the fact that it just kind of stays on the same, linear curve. So, if we move things around, what we'll get is that p is something like 1 over 2t. Well, not exactly. It's like one over 2t plus something that's, up to a multiplicative factor, something that goes to 1 as dt goes to 0. But we will just ignore this, because it's going to go to 0 in all of the calculations. So, conveniently, I'll just assume that it's just the probability to jump is just exactly 1 over 2t. Okay? So I have a probability of 1 over 2t to jump distance minus 2t. And, the rest, which is like, sorry, I'm sorry about it. It's dt over 2t. So I have a probability of dt over 2t to jump a distance that looks like minus 2t, which is jumping from something like plus t to minus t. And then the rest, which is 1 minus this O of dt, to, jump something that only looks like dt. And, these two things are 0 up to O of dt squared. Okay. So you can just, in a sense, this formula just completely determines what this process is. So this process is just, it's going on one of these two lines, and then in each, infinitesimal interval of length dt, I have this probability of dt over 2t to jump to the other side. And note that, the function 1 over 2t diverges near 0. So 1 over 2t, this integral diverges near 0. And that means that when we get close to 0 here, it's going to jump an infinite amount of times. But it's actually integrable when we go to, when we are bounded away from 0, meaning that between any point here and 1, there is only going to be finitely many jumps. Let me just wait 5 seconds to see if there are questions about this process. Okay, so you can like literally think of dt as being a small number, and then, it's a process that either moves like a very small distance, like dt, or jumps to the other side, but this happens with a much smaller probability. Okay, good. Now, so we have this process, and now let me go back to a little bit for what we had before. So suppose that xt, so suppose that xt is any martingale satisfying that x0 is 0 and x1 is 1, is, 1 in absolute value. So it's just a way to sample a random bit. So I can define just the vector value process xt such that xi of t has the distribution of like this process. So let's just say all the coordinates are IID with law of, the process xt. So you just take, n independent copies of this martingale. So now we get a martingale, not in the interval -1, 1, but in the continuous hypercube, -1, 1 to the n. Okay, so this is a martingale -1 to the n. And, for f multilinear extension of a Boolean function, but actually of any function, we can define the martingale mt to be equal to f of xt. So just recall, before we had a very specific and simple martingale that, started from the center here, and at every iteration, we had a discrete time axis, and at every iteration, we picked a coordinate, and then we moved to ±1 on this coordinate until we ended in a corner. Now, we just say, okay, this is more general. I can take any martingale in -1, 1. I take independent copies of it, and I plug, this thing into the multilinear extension. And I claim that, MT constructed this way is always a martingale, regardless of, what the process xt was. And the reason is that if I take f, I can just write f of this vector as the sum, just the Fourier decomposition of these sums and it's enough to show that each such product is a martingale. So enough to show that for every A, those guys are martingales, and for all A, this product, sorry, this is I in A, this product is a product of independent martingales. And it's a one-line exercise to show that a product of independent martingales is a martingale. And also the sum of martingales is a martingale. So MT is a martingale. Okay? Now, recall that in the proof of the Poincare inequality, what we basically said is, okay, if I have a martingale, a very natural thing to look at is the sum of square differences of this martingale. And this is always going to be equal to the variance, right? This is basically just, I guess sometimes it's called Ito's isometry, or I guess it also has a name in discrete time, which I don't remember. So when time is continuous, it's not very clear. So we want some notion. Recall that when the time was discrete, we had this notion of sum of differences that looked like this. But now time is continuous. So the question is there, an analog of this quantity? And the answer is yes. When the time is continuous, you can just take some limit. So this is called quadratic variation. It's kind of like a canonical property of any martingale, and in particular continuous martingales or jump martingales. So for any really stochastic process MT, we're going to define its quadratic variation M with those square brackets T as the limit as epsilon goes to 0 of this exact same thing, only I sum over a grid of size epsilon. So let's just take the sum over all T, or I already have T, sorry, all S in the interval 0T intersection with epsilon times the integers. And then take here ms minus ms plus epsilon squared. So this is just, the sum of squares of jumps. And it's not clear a priori that, this limit actually exists, but it turns out that it always exists when we have a martingale, and I think we're going to more or less see why this is the case later. And now Ito's isometry is telling us, and the proof is basically exactly the proof we saw before with a little bit of extra technical details, that the variance of m at time t may be conditioned. Okay, sorry, I think I have no choice, but no, okay, no, okay. I'm gonna avoid defining filtrations still. The variance of m at time t is just equal, or maybe let me say it, minus m at time s for any t in s. Is equal to the expectation, the difference between the quadratic variation at time s and the quadratic variation at time t. So it's just the expectation of the sum of square differences. It's kind of like the generalization of what we saw before. Okay, great. So all this is like very general. I mean, it's true for any martingale. And now let's try to see what it means for the martingale we just defined here. Okay. So if we take, t to be 1 and s to be 0 in this formula, then the left-hand side is just the variance of f, which, as you remember, we usually want to bound. I mean, I didn't say what we're trying to prove, but we are usually proving some kind of concentration inequality. So we want an upper bound of the variance of f, usually. And, by Ito's isometry, this is just equal to the expectation of the quadratic variation of the martingale time 1. And this is, true for any way to sample those random bits. So if we just sample them as in the proof of the Poincare inequality, we exactly get what we saw above, which is just those sums of squares differences. But now let's look at this jump process and see and try to understand what the quadratic variation means in this case. So in this case, time is continuous. So let's write this thing as an integral from 0 to 1 of the expectation of m at time t plus dt. I'm being slightly informal here, but again, think of dt as being, just a small number. So this is just a telescopic sum, or a telescopic integral, if you want. And now let's try to understand what is the difference in quadratic variation between the martingale at time t plus dt and the martingale at time t. So yeah. So maybe, let me do one more step here. This is basically equal to the integral between 0 and 1 of the expectation of m t plus dt minus m t squared sorry, and I don't need to write a dt here because this is already in infinitesimal. And also here, I don't need to write dt. This thing is really the order of dt, right? So this is equal to the integral between 0 and 1 of, so m was f of xt, so it's just the expectation of f at x t plus dt minus f at x t squared. Sorry. Let me just move this a tiny bit. So okay. And let's try to understand what this thing is. Okay. So first of all, if there is no jump, if none of the coordinates of x jumped at all, then xt plus dt, its distance from xt, if no coordinates jumped, then xt plus dt minus xt is, or maybe like the norm of this is O of dt. And since f is Lipschitz or continuous, or I mean, it's Lipschitz, then this means that f at x, sorry, I mean, t plus dt, t, f at xt plus dt minus f at xt is also, O of dt. I'm not sure what's happening. Something is still weird with my eye. Sorry about that. Which means that if I square it, I get dt squared. So, this thing squared is little o of dt. So when we integrate it, we just get 0. So we kind of only care about the jumps. Now, if dt is small, only one coordinate is going to, jump at most. Unless, so the probability that more than one coordinate jumps between t and t plus dt is also, if the coordinates are independent and each coordinate has probability order dt to jump, this is also little o dt. It's again like dt squared. So we can really ignore the contribution coming from the case where no coordinates jumped and the case that more than one coordinate is jumped. So we only care about the contribution of coming from the case that exactly one coordinate made a jump. So this is going to be equal to the integral between 0 and 1. And now I sum over all coordinates. And I take the probability that xi of t jumped between t and t plus dt. And when this coordinate jumped, by how much, okay, given that this coordinate jumped, what is the value of this difference? Well, I claim that it's basically the derivative in the ith coordinate of f at xt times the distance of the jump, which is equal to 2t squared. Any questions about, so, I kind of hand wave this, but hopefully it's intuitive enough. Any questions about like this equality? Okay. And now we know what the probability is for a coordinate to jump. It looks like we calculated, or at least more or less calculated, that it's equal to dt over 2t. So I'm just going to replace this by dt over 2t. And what I get is the integral between 0 and 1, sum over coordinates, dt over 2t, del if xt. Sorry, I forgot the expectation. And there's also an expectation here. dt over 2t, del if xt times 2t squared, which is just equal to the expectation, the integral between 0 and 1 of the gradient of f at xt norm squared, 2t squared over 2t just gives me 2t, so times t dt. Okay, so we got a formula for the variance of f in terms of what? In terms of the norm of the gradient of f at various points inside the continuous hypercube. Okay, and this is like very close to the formula we saw before when we proved the Poincare inequality, that basically said that, yeah, so this formula, so the variance of f was equal to the sum of those squares, which in turn were equal to something that has to do with the partial derivatives of f evaluated along this process xt. So now we just have another process, but the principle is exactly the same. And really, for any martingale we define, or for any sampling procedure we define, we're going to automatically get a corresponding representation for the variance. So this is just the representation for the variance coming from this particular martingale that is the jump process. Okay. Good. So now let's try to use this thing in order to show or maybe let's summarize just a little bit. We have that the variance of f is equal to the expectation of the quadratic variation of m at time 1. And really what we established here is that the expectation of d of the quadratic variation at any time t is equal to dt times t times the expectation of the gradient of f at xt squared. So if you want, like, I think a good intuition for this, so d of the quadratic variations, the instantaneous change in quadratic variation is just telling us how fast this martingale MT is moving. So it's kind of like how much information I'm getting about the value of f when I go from t to t plus dt. And it's equal to just...
Are you missing a factor of 2?
I am missing the factor of 2. Thanks. And the instantaneous, basically the speed of the martingale MT just depends on, how big the gradient of f is at the point xt. Okay, and usually when we prove concentration inequalities, we want, like, concentration inequalities usually have to do with the variance on one side and things that have to do with, like, local changes of f, so that, like, the derivatives of f, but not at xt, but, at x1. So when we reach all the way to x1. So this is going to be helpful for us. And as an exercise, I want to now show you how to prove this theorem by Talagrand. We'll actually prove 2 theorems by Talagrand. So this is, I think, from 94 or something like this, which is an improvement on the Poincare inequality. So the Poincare inequality says that, the variance of f is at most, let me write it like this, the expectation of the gradient squared of f, right? This is just like the sum of influences. So Talagrand proved, so this is Poincare. Talagrand proved basically that I can remove the square here, which only makes this smaller because, each partial derivative is either -1, 0, or 1. So, when I square it, yeah, so the gradient square has to be an integer, meaning that when I take the square root, I only make it smaller. up to some constant. Okay, if this doesn't look familiar, sometimes this thing is also called, denoted by the expectation of the sensitivity of f, where the sensitivity of f is just how many coordinates the square root of the sensitivity of f, where the sensitivity of f is how many coordinates I can toggle, and this is going to toggle the value of f at the point. Brackets. This doesn't sound familiar. Okay, and now let's try to prove this fact. So we're going to use this representation. So, I just want to bound this integral by this. And the main lemma is going to be the following thing. Okay, actually, yeah. So the main lemma is going to be that I'm going to fix some universal constant whose value will be chosen later. Okay, let's just do it like that. Sorry, I'm a bit messy today. Let's define a stopping time tau to be the minimal time t such that the norm of the gradient of f at xt is at least this constant. And our main lemma is going to be, maybe let me write it like this. So minimum with plus infinity. So it could be that this event never happens. If this event never happens, I just, define tau to be plus infinity. And the main lemma is going to be that the probability that tau is less than infinity, actually let's call this 1. Because anyway, time is between 0 and 1. I just want to keep the notation as kind of the least confusing.
Want tau to be an infimum?
What?
You want tau to be an infimum?
Again, sorry, I couldn't hear you.
Do you want tau to be an infimum or a minimum?
It doesn't matter. Yeah, it does matter. Well, I didn't really say. Let's say infinite. Okay. Sure. This is not continuous, and I actually did not say whether the process xt is right or left continuous. So at the point of the jump, it's not clear, if you've already jumped or not. So let's just write infimum. So I want to say that the probability that tau is less than 1 is at least some other constant c prime times the variance of f. Meaning that, the probability that there is a time where the gradient is at least order a constant is at least, some constant times the variance of f. So let's now see why the lemma implies the theorem. So the main fact we're going to use here is, again, recall that xt is a martingale with IID coordinates, which we already saw that this implies that the gradient of f at xt is also a martingale. Remember, because each coordinate of the gradient of f is in itself a multilinear function, so we can just take the Fourier decomposition. I mean, it's just the sum of products of independent martingales. And then Jensen's inequality implies that the expectation of, so maybe the Euclidean norm is a convex function, and therefore Jensen's inequality implies that the expectation of the norm of the gradient of f at x1 is bigger or equal given x at the stopping time tau is bigger or equal than the norm of the gradient of f at x tau. Right. So now we have that the expectation of the gradient of f at x1 which is equal to the right-hand side of the inequality we want to prove, right? We wanted to prove that this is big. So this is bigger or equal than the expectation of the indicator that the stopping time tau is less than 1 times the norm of the gradient of f at x at this time tau. But by definition, this thing is bigger than some constant c, by definition of the stopping time, right? So that's bigger or equal than the probability that tau is less than 1, which is, by the lemma, bigger or equal than, sorry, there's a c here. Which is, by the lemma, bigger than c times c prime times the variance of it.
tau less than 1.
Sorry?
Should be probability of the tau is
Sure.
less.
Sorry. Strictly less than 1. Thank you. Okay. Right, so all we want to show is this lemma. And this lemma really follows from, I mean, a completely general lemma about martingales. So let's call it lemma prime. If MT is any martingale, such that M at time 1 is, maybe I don't even, any martingale such that M at time 1 is always plus minus 1, and MT in absolute value is less than 1 for all t, which our martingale satisfies, then the probability that, maybe let me write it like that, no, that's, then the probability that the quadratic variation of M at time 1 is bigger than some constant, so there exists a universal constant, is at least this constant times the variance of M1. So what does this lemma say? This lemma says, recall that we know by Ito's isometry that the expectation of the quadratic variation time 1 is equal to the variance of M1. So this lemma says a bit, I mean, it just says, not only in expectation the quadratic variation is big, but also there's a non-negligible probability that the quadratic variation is bigger than a constant. It couldn't be that the fact that this expectation is big is only due to a very small probability event in which the quadratic variation is, is just huge. It's actually quite likely that the quadratic variation will be, bigger than something. Now, we'll take a break in 1 minute, but let's see how lemma prime implies, okay, maybe let me call it lemma, okay, how lemma prime implies lemma A. So why does B imply A? Well, the quadratic variation of M at time 1 is just the integral of t times the gradient of f squared xt. Okay, you know what? I I need to let's take a break. And I mean, okay, ideologically, it's this, and if whenever this is bigger than a constant, there must be like an instant where this is also bigger than constant. Only this equality is not exactly true. It's true in expectation, but it's not exactly true without an expectation. So let's leave this for the next, for after the break.
Thank you. Any questions for Ronen?
So in lemma prime, I was confused about the definition of MT. Like, so you said that MT is in plus minus one, but then also the magnitude is bounded by one for all t. So
sorry. M1. Yeah, I'm really glad some people are paying attention. Sorry. It's a martingale so think about f of xt. What do we know about it? At time one, at the final time, this is a Boolean function, so it has to be plus minus one. And at any given time, it's somewhere in between, and it starts from the expectation of f. Sorry, this has to be, yeah. Thanks.
Yes.
Yeah, that's some more questions.
Yeah. The coordinate reveal process, right? It's kind of giving you conditional, like when you're doing the process, it's kind of giving you conditional expectations of f.
Right.
So when you're doing this process, what are the? I mean, you're getting some information about f, but like what kind of? I don't know. It's different, but what kind of information is this? So that's one question. The second thing is how do you choose this process, in the sense that you have this process, like say I'm trying to bound the variance, and somehow I'm thinking of this process as like writing down an expression of some nature, and somehow this particular process seems to be more effective, right? So where is that, how do you sense that some choice of process is more effective, in getting okay, yeah.
So later on, it's going to, okay, so let me answer your first question first. So, it's still some conditional expectation. It's always the case that, right, that like f of xt, I mean, I should have said it, but so thanks for pointing this out. It's a martingale. It's always, the conditional expectation of f of x1 given xt. So the coordinate revealment process, xt was like on these points, and now xt is going to be like, here, and then here, and then here, etc. So I mean, I'm not sure I have anything else to say about it, but each of these processes gives rise to a sequence of conditional expectations. Now, why is the process of the red points better than the process of like the green points? So we are actually, we haven't used it yet, but we are actually going to use the fact that later on, that like the norm of every coordinate is always t. So if you want, this is kind of like this is very related to the notion of noise stability. So it's not hard to see that the expectation of f of xt squared is just equal to stab t of it. So we're not going to use this directly, but ideologically this will be kind of something we'll use. I don't know.
Yeah, thanks. There was one more question.
Yeah, hi. So I was thinking like you can sort of couple the green point and the red point, right? Like, because you only jump like finite many times after like t larger than epsilon. So you can think of it as like first sample a random point on the epsilon cube, and then you sample a bunch of random coordinates to jump. And then sort of the green process and the red process becomes the same. And
wait. I don't see how to couple them actually. Can you?
Oh, I'm saying like, it's not a coupling, but there's some corresponding like, you can define them in the same probability space in the following way. First, you sample. So because after t larger than epsilon, there's only going to be finitely many jumps. So you could just think of it as I just start at t equals epsilon. So I sample a random point.
That's not a problem. So we start like here.
Yeah. We sample a random point on the epsilon cube.
Yeah,
and
sure.
Then there will only be a finite number of jumps. So I could just define
for every coordinate a finite number of jumps. Sure.
Yeah, but I only have n coordinates. So, and I can define a discrete process, which each time it picks one coordinate, one random coordinate, and then it jumps in that coordinate, like flip the sign. And
but it's not going to be with probability half and half anymore, right? Because you've already revealed a little bit of like what the coordinate is going to be.
Oh, yeah, that's true. I see. Yeah. But I guess like you can also discretize this red process, and it becomes discrete just like the green one.
Yeah, you can take dt to be, dt doesn't have to be infinitesimal, but it's going to be convenient for us later on.
Yeah, I see. Thanks.
Any final questions? Let's thank Ronen again. We'll reconvene at 2. Yeah, see you.